Welcome back, everyone. Uh, my name is Bharat, and I'm going to continue with our previous session, the session on the distributed deep learning. The session is going to concentrate or continue with the concepts that we saw in the last lecture. So again, we will look at the concepts that we explained in a bit uh, in terms of the theory, and then I will continue with hands-on session where we are going to show you a demo of all the concepts that were explained. So the first thing that we talked about during the session was also the necessity of understanding the system topology. We introduced you to two particular concepts, latency and throughput. Latency is nothing but the time taken for the transfer of a single packet of data. How much time does it take for me to reach from one destination to the other? The second one is throughput. Throughput is the quantity of data that can be transferred in 1 unit of time. Like, can I transfer 1 KB of data, 2 KB of data, 3 KB, and all. And it is important from a point of view of scaling. The scaling laws kind of define, and they would be dependent on the system on which you are going to run the multi-GPU or any kind of a distributed deep learning jobs. And we saw a particular system architecture, which I explained in the last call, which is one of the NVIDIA system called as NVIDIA DGX. NVIDIA DGX system consists of two CPUs, CPU 0 and CPU 1. It consists of a couple of PCI switches, and it also has 8 GPUs. These 8 GPUs are connected to each other via interconnects like NVLink. If you want to go across nodes to different nodes, you get connected via NIC cards or InfiniBand, which will connect to the other machines as well. We are going to do hands-on in this particular session on a DGX machine itself. There is a particular concept that we explained yesterday, which is referred to as GPU direct. In this case, you can see there is GPU 0 and GPU 1. No matter what kind of a communication method you use, whether data parallel or model parallel, whenever you want to communicate, if you are able to do direct communication between GPU 0 and GPU 1, referred to as peer-to-peer transfer, directly without involving CPU, hence reducing the latency, is referred to as GPU direct. It is only possible under certain scenarios, which we will see in the hands-on session again. We also talked about NVIDIA Collective Communication Library. NVIDIA Collective Communication Library is a library or a framework which has been built by NVIDIA, which helps in doing, as the name says, collective communications. It is a library which is integrated into all of the frameworks like PyTorch, TensorFlow, and all to effectively do the multi-GPU. When you enable multi-GPU distributed training, NCCL is called behind the scenes, and we will look at how to see or how to even be assured that this is happening. It has various advantages, which we have talked about yesterday. Like, it is basically something which does different kinds of detection graph. It does graph analysis to find the shortest path, the path having lowest latency and highest bandwidth. It does automatic topology detections, and hence it helps in scaling pretty well on different kinds of clusters. We talked about two different kinds of parallelism whenever you want to go from one GPU to multiple GPUs. The first kind of a parallelism is referred to as the model parallelism. The second one is data parallelism. In the model parallelism, you would split the model or the layers across different workers, each worker accessing a particular separate GPU. Worker, the model parallelism is particularly more difficult, and it is primarily used especially when you cannot fit the whole model into one particular GPU memory. GPUs nowadays come with almost 80 GB of memory. If you're talking about models, nowadays you have models till few trillion parameters. In that case, it is almost impossible to fit them into one GPU. So you need to make use of model parallelism. Data parallelism is a way in which you take one model and replicate it across all the workers, each having their separate GPU. What you're splitting basically is different batches of data, input data, which would be required for training. These two methods can be combined together into hybrid model. In a hybrid model, you combine both worker parallelism and data parallelism together to enable real world problem solving, especially when your model is large and the data set is also pretty large. In that case, you can combine both of them as well. The next thing we also said is whether it is no matter what type of parallelism, you can do it either in a synchronous fashion or asynchronous fashion. In a synchronous fashion point of view, each variable in the model is mirrored across all the replicas, and these variables are kept in sync with each other and by applying identical updates. So at every step, when you have given the respect to, like in case of data parallelism, whenever you are basically updating the gradients, they are basically at every step, they get exchanged with each and every worker in a synchronous fashion, and then they continue to the next step. While in asynchronous communication, there might be different methods. You don't need to be always at a synchronous step. The variables can be created on a separate server, which can be also referred to as a parameter server. And all the workers, they basically can read and update these variables independently without synchronizing with each other. And that's what we saw is a method of asynchronous programming. We said in the last session that no matter what method it is, or whether we want to use GPUs, all of the existing frameworks support the same. You have TensorFlow, you have Horoword, PyTorch, MXNet, all of them supporting multi-GPU, and they all have different methods for doing data parallelism, model parallelism, and a hybrid parallelism approach as well. Today, we'll try to touch on one or more of them. In the today's demo, again, in the session 1 of this particular series, we touched upon the usage of container and how we can utilize or download the containers from NVIDIA GPU Cloud. In the today's session, again, we are going to use containers, and this container would be running on a DGX machine, and we have built this container and we will be using Docker for running this container, and it has been pulled from the NGC repository. So in case you have missed that session, we recommend you to definitely look at the NGC session, which was delivered in session 1. So let me start by showing you a particular demo. So as you can see here, I have already set up a particular server. In this server, I'm basically running a Docker container, and I have already forwarded it to my machine. So all of the materials that you are seeing here, they are all been made open source, and we will be putting the link to the material by the end of tomorrow's session into the Slack channel, and you would be able to download this hands-on material as well. If you have access to any of the multi-GPU machine, you would be able to replicate it and run it inside a container environment. The first thing I would like to show you is the machine itself. So if I do NVIDIA SMI command, which was shown to you previously also, you can see that this machine basically has 8 GPUs. The 8 GPUs are of type Tesla V100. and they are all currently 0% utilized at this time. So let us get started, and I'm going to start with certain theory once more of distributed deep learning, and then we will move towards the part of just give me a second, I need to somehow, yeah. So we already talked about some of these fundamentals, so we will quickly skip that. But what I'm going to do is I will give you an overview of some of the hyperparameters that you can do to improve the performance of your existing models. So here I'm basically running or calculating the throughput of training of a natural language processing model, which is referred to as GPT here. And we are going to try a hyperparameter called as batch size, which will kind of define in terms of how much performance we can get by tuning these hyperparameters themselves. So it will take some time to finish. By the time it finishes, you would see something like this. If I have a batch size of 32, the throughput for me is around 1050. The same, if I change my batch size to 64, I will see that my throughput basically increases to 1498. And if I change my batch size to 128, which means I am able to give it a larger input, in that particular case, my throughput will increase from 1906 to 2192, and it keeps on increasing till the time it saturates at 1280 batch size. What does it mean? Is something that you can try to get more performance on a single GPU by also trying out certain hyperparameters like the batch size. Generally, GPUs, as we said earlier, are basically massively parallel architectures, and if you give them much more higher batch sizes or much more parallelism, then in that case, they will give you more performance within the single GPU environment itself. So let's just wait for to see the 32, and then we will directly jump to 1024 to show you. So you can see here the units per second is kind of consistent at 1058.55, which is the throughput of my current training. So I'm running a model called a GPT, which is a natural language processing model. It's quite a large model, actually. If you do the same on a sequential processing unit, you might end up maybe taking day to finish the same job. So as you can see, it kind of saturated at 1072. So let me just change the batch size and make it as 1024 for training the model. And let's see what happens. Can one of the organizers confirm if they are able to see my screen and they're able to see the Jupyter notebook running?
Yes, sir, we can see it.
Okay, thank you. Right, so you can see here, previously when we had run it, it was around 1078. When I increased the batch size, you can see here that the overall time, the throughput doubled. It went to 2529, which itself is a very huge difference, but just by changing a hyperparameter called as batch size. But as we had discussed last time, that the models are becoming larger and larger, and we are able to not able to train it on a single GPU because of the memory constraints or time constraints, and we would like to utilize many GPUs. And you can see here an example of a weak scaling in terms of images per second across so many GPUs. We are reaching almost utilizing 30,000 GPUs for this particular example here, for running a particular training. Now, we talked about distributed deep learning, but distributed deep learning particularly is not just limited to training phase of artificial intelligence. The same can be done at the inferencing stage also. Just to recap, in an artificial deep learning phase, you have two stages. The first one is the training phase, where you're trying to learn the parameters. And then finally, once you have the model trained, you're going to deploy it and inference. You can use distributed deep learning for both training as well as for inferencing. Like for inferencing, we have another systems like NVIDIA DeepStream, which can help you in scaling your inferencing part of it. Today, we are going to focus just on the training part of it using two frameworks and cover some of the fundamentals. We talked about the model parallelism part, and we also talked about the data parallelism part. We talked about synchronous and asynchronous communication as well. So all of the frameworks, as I said, kind of support this, and we are going to look into those details later on. But let us define, what do we mean by when I start using more number of GPUs? Am I efficient or not efficient? Or the definition of scalability or scaling efficiency. So here we are defining the scaling efficiency as the total number of processed per unit time. So how many of the samples are we processing per unit of time divided by the number of GPUs, and the overall thing divided by the samples processed per unit per GPU, which means I'm trying to do the processing for a GPU which has lesser amount of load because you have scaled it across, divided by the number of samples that you would have done in a single GPU when you had only one single GPU. And that kind of defines the efficiency. Am I scaling at 85% efficiency? To give an example, suppose I was able to do 1000 samples per second in a single GPU. When I go to 2 GPU, ideally in 100% scaling, I should do 2000 samples per second. But if I'm not doing 2000 samples per second, if it will reduce to 85% or 95% based on this particular formula that we have. So here we are showing you the concept of scaling for the fashion MNIT dataset using synchronous training using a framework called as Forward. We are going to see how to use Forward later on also, but here what we are talking about is the efficiency. The first thing I'm doing is we are going to run one GPU, and I've enabled certain logs to make sure that we are able to get more details when we are running this. And also, as you can see, there are certain additional parameters. We'll talk about those additional parameters later on, but we are running it on a fashion MNIST for a synchronous data set, and we have converged on the batch size. We are using the same batch size, which is 2048. So I'm going to run using only one GPU, even though I have 8 GPUs with me. So you can see here, when I use one GPU to train a fashion MNIST data set on a GPU, it is giving a throughput of images per second of 67,758, right? Now, without changing anything, I am just going to provide it with more GPUs. In this case, I am talking about running it across 2 GPUs. And ideally, I expect it to give double the images per second to me. So you can see here, it has gone to almost 1,42,000 images per second, and I can train much more faster when I added one more GPU to it. What if I had 4? So you can see here it increased from 1,42,704 to 2,35,271, and it kind of continues. And I am now utilizing all of the 8 GPUs which are there. So in general, this number would change from one machine to the other based on the kind of topology you have, and we are going to go into the details of how that works. So it increases from 2,35,000 to 3,81,000. By now you would have observed that ideally, if it was scaling at 100% efficiency, I should have got some 4 lakh something, right? But it is not scaling at that rate, and that's what we were referring to above. So the numbers, the scaling efficiency when you go from 1 GPU to 2 GPU to 4 to 8 is scaling at a particular efficiency. And this is how you can also measure how well you are able to scale when you keep on adding more and more. And with more and more GPUs being added, the idea is that you end up doing faster training without having to compromise on the accuracy. Now, there are cases where your accuracy gets compromised, and that's what we will cover in the last session.